Okay, so here's a little video about K sub W, the auto-ionization constant in water, and what can we use it for? Why do we care? So first off, the auto-ionization constant of water is K sub W. It's an equilibrium constant, just like any other equilibrium constant. It's just that water is pretty important for us in chemistry, and so we pay a little particular attention to it. But like any equilibrium constant, we're going to start off with a or equilibrium expression. We got to start off with a balanced chemical equation. So what are we looking at here? Well, we're looking at the fact that pure water on its own sometimes breaks down into some hydronium and some hydroxide. And in addition, that some of this hydrogen and hydroxide, when we reach equilibrium, will turn back into water. And so this is a reversible reaction. At any point, some water is breaking down into these two things, and some of these things are recombining to form water. Again, when the rates of those two actions are happening in equal directions, but at the or in opposite reactions, but at equal rate, then we have achieved equilibrium. So if we have some water at equilibrium, we might want to know, well, just in normal water, just glass of pure water, how much of that is hydrogen ion and how much of that is hydroxide ion at any given temperature, because like any KEQ, this would change with temperature. And so we're going to start off, and we're going to look at an equilibrium expression for this. And so we have some, just to put the states down because this will help us with the next part, we have some liquid water that's breaking down into some of this ion that's dissolved in the liquid water, making it aqueous, and some of this ion that's dissolved in the liquid water, making it aqueous. So if we wanted to write a general equilibrium expression for this, we're going to say, well, any KEQ, any general KEQ, is going to be the concentration of the products over the concentration of the reactants. But remember, in KEQ problems, or equilibrium problems, we only pay attention to gases or aqueous things because liquids have a concentration, a pure concentration, a concentration of 1. And so we could write that into this expression, but it would end up being just divided by 1. And so we're going to leave out the water. It's a liquid. These two items, though, are both aqueous. And so we can say that for water, the KEQ would equal the concentration of hydrogen times the concentration of hydroxide. And now this is going to be kind of a useful form for us because this value for KEQ has been experimentally determined at a range of temperatures. We're going to assume that the temperature changes not significant enough that we can use this as a constant. It's kind of beyond the scope of our class to start looking at changing this. And so we are going to say that the known value for K sub W is going to be 1 times 10 to the negative 14th. Okay? And we're going to, it's actually slightly less than that at room temperature, but again, we're just going to say that this works at, it's going to be precise enough for our class, for our purposes, to work at any normal range of temperature. We can then substitute that number in for our K sub KEQ, and we can say, well, 1 times 10 to the negative 14th is going to be the amount of the concentration of H plus and the amount of concentration of OH minus multiplied by each other. And actually, we know the values of these things in addition. they are each 1 times 10 to the negative 7th. And that should make some sense because they have to be equal to each other just in pure water when water auto-ionizes. And that's what this number is for, is when water auto-ionizes. It's 1 times 10 to the negative 14th. But one of the cool things about this is this generalized KEQ expression can work even when we start taking away or altering, I should say, the concentration of some of these ions present in the liquid. And so there's always going to be a balance. Our KEQ isn't going to change, just like the equilibrium constant doesn't change if we added some. Remember when we did Le Chatelier's problems, if we added a substance, it doesn't change the equilibrium expression. Instead, the reaction acts to reduce that amount and raise the amount of the other thing so that the equilibrium expression can remain constant. So if we add one of these ions to this, it's not going to change our number. This 1 times 10 to the 14th, even though it comes out of the auto-ionization constant for water, or auto-ionization water, is going to be a number that can be used for us in any problem. And it's going to allow us to translate from the concentration of hydrogen directly to the concentration of hydroxide or vice versa. And so to see that in practice, what we could do is say if I've got a solution with a concentration, let's say, let's start with H plus. Okay, and let's say I've got 0.004 molar hydrochloric acid or something I'm throwing in here as my hydronium supply. And I want to find out, well, what is the concentration of my hydroxide? Well, the K sub W gives us a really easy way to go between those two things. I can just say that, well, 1 times 10 to the negative 14th equals 0.004 times X, whereas X would represent then the concentration of the hydroxide. And so I can see that if I take 1 times 10 to the negative 14th and I divide it by 0.004, I should get some 2.5 times 10 to the negative 12th molarity for my hydroxide. And so boom, done, easy. And this is probably a little bit easier route than going through pHs and that, which can be done. But this just kind of allows you an abbreviated way to move between hydrogen and hydroxide. And so as far as useful skills of K sub W, this one right there is probably your most useful, just allowing you to directly go between those concentrations. Just to prove that this works, let's take a look at this and, show a couple of other of these kind of acid-base strategies using the same problem. Let's solve this problem in a different fashion and just make sure that our answers are consistent. Okay, so we said that we had some H plus concentration of 0.004 molar. I can get to the concentration at OH through a pH and pOH route. And so let's do that and just make sure that we come out with the same 2.5 times 10 to the negative 12 molarity. First off, I can say that I know on the definition of pH, it's the negative logarithm of the H plus concentration. So in this particular case, it'd be the negative logarithm of 0.004, which would be 2.4. Okay. One of the other things we also know is that pH plus pOH always have to add up to be 14. That actually comes out of this ionization constant, but I don't want to get into why or how because it's not useful for us. But we do know that these two things add up to be 14. So if we got one of them, we can always find the other. Well, if we say what plus 2.4 equals 14, or 14 minus 2.4, we find out that our pOH is 11.6. Now that we have pOH, we've got another useful formula for us that says that the concentration of the hydroxide ion is going to be equal to 10, sorry, to the negative pOH. And so here we have 10 to the negative 11.6. And if you run that through your calculator, you will find out that indeed we get the same answer no matter which strategy we pursue. So this is just kind of a little easier. That K sub W is a little bit easier around probably on a problem when you're moving directly from one concentration to another. This kind of strategy here is probably more flexible because this, as long as we remember these 5 formulas or have these 5 formulas at our fingertips, we can solve really any sort of hydroxide or hydronium problem. That pH equals negative log of H plus, and that there's a corresponding formula for pOH. And that if we want to go the other direction, if we're given H plus, or excuse me, we're given the pH and we want to find H plus, it would be 10 to the negative pH. And if we are given the pOH and we want to find the hydroxide concentration, that's 10 to the negative pOH. And so you can see there's really only 2 formulas here. It's just that they work for H to pH or OH to pOH. And then the last fact is that, pH plus pOH always have to equal 14. So these 5 formulas here can solve anything on their own, but this one for K sub W can just help us, again, skip some steps in order to move directly from one concentration to the other without having to go through, all these multiple steps. Conceptually, this shouldn't be too hard, hopefully. But it's multiple steps, and anytime we have multiple steps, well, there's more room for error. So here are your keys for the kingdom as far as pH, pOH, H plus concentration, OH minus concentration, and the auto-ionization of constant of water and kind of how that ties in here. I hope that addresses your questions. If not, let me know, and I certainly can, with a little more specificity, and I can certainly address whatever concern you have.